Okay. Good morning, students. We'll start the class. Okay. So, in the last class, we were discussing about the numericals of the induction machine. Numericals on the induction machine. Today, we will proceed that concept or proceed that numerical. That how, what what are the things that we have developed. Okay. So, in this way, we were discussing about the induction machine's numerical. On that topic, we already have completed our two simple numericals that is related with your rotor frequency, synchronous speed. This was our first example that we have completed, in which a rating of the machine is given, then the voltage, supply voltage is given, then frequency already given, number of poles, connection, then delivery output, output power is given, the sleep value is given. So depending upon the available parameters, we had to calculate three components: synchronous speed, rotor speed, and frequency of the rotor current. Rotor current. So from the appropriate formula, we have derived the different types of numericals. So then we have also seen this numerical as there is another term called sleep speed. So with the value of the use of the proper formula, we have also derived the sleep speed as n sleep equal to s into ns. S into ns is the sleep into synchronous speed. That will give you the sleep speed. Okay. So we have already done the two types of numerical based on the induction machine. So now let us move to this was our equivalent circuit diagram, in which this is your primary side and this is your secondary side part. Primary side components, this is the core part of the induction machine, and this is the rotor part of the induction machine. Here you can see it is quite similar to that of a transform. It is quite similar to that of a transformer, where this is your VL, or you can say primary side voltage. Then there is a primary current is flowing in the rotor side. Then there is a stator resistance, or you can say primary side resistance. Then there is a stator reactance, or primary side reactance. Then there is exciting current, a magnetizing current, core loss current. This is the core loss resistance. This is the magnetizing reactance. So these are all correlated with your stator of the induction machine. Now, when you compare this primary side circuit with your transformer circuit, it is identical. It is quite identical. Here also, this IE is your exciting current in the similar manner in that of a transformer. Here, this IE is 25 to 30% of the no load current. But in case of transformer, this IE, or you can say no load current, the value is only 5 to 10% of the rated current. Okay, because of the air gap, this no load current is increased in case of your induction machine. But in the transformer, there is no air gap provided, because there is no rotating machines is given, so the no load current is reduced. In the similar manner, this is the primary induced EMF that is given here. Now this is the air gap. This is the EMF induced in the air gap, that is ER, or you can say the EMF induced in the rotor part is called E2. You can write it as E2. So in the rotor part, this is the short circuit condition. When you want to put a load, you can provide in the secondary side inductive capacitive or resistive load here. Here it is taken as the short circuit condition. So in the rotor part, the current flowing is your I2, or you can say IR. Then there is a rotor resistance, that is IRR, or this is a rotor reactance, that is ZXSR. So depending upon this equivalent circuit diagram, we have to do some numerical. Now the EMF induced that we have discussed, the EMF induced in the rotor or the induction machine is given by this formula. Only this NR is included. Only this NR is included, quite similar to that of a transformer. In the similar manner, here you can see that normally the ER not equal to the EMF induced in the induced voltage in the rotor part is given by this formula. As you can say, root 2 pi F. When you multiply with form factor, you will get 4.44 NR pi M Fe. Okay. Here also Fe is the supply frequency. Fe is the here Fr equal to F at the standstill condition. But in running condition, this Fe will be converted into S into Fe. That is the rotor winding EMF. Rotor winding EMF will become this one. Okay. So this is your standstill in EMF induced in the rotor part. But when you rotate the machine, it will be multiplied with the slip value. Okay. So this is the rotor circuit was given. This is the another rotor circuit. When you combine both of these, you will get this one. You will get this one. In there is inclusion of your slip with the rotor resistance part that we have discussed already. These are already discussed in our previous class. Power flow equation is also we have discussed in the previous classes. So here you can see that there is another numerical there is another numerical given as is, for example, one. You can see that 480 volt is provided. That is supply voltage. The supply frequency is your 60 hertz. The number of poles is 6 pole. Okay, the number of pole is 6 pole. Then there is a three-phase connection. This is not a single phase connection. This is a three-phase connection. The three-phase connection will have RYB and neutral will be there. Okay. Now it is very important. Here you can see this is a delta connection. Delta connection means there will be line current equal to √3 into phase current, and line voltage will be equal to phase voltage. Okay, this is the delta connection characteristics. Now, induction motors have another parameter, that is primary or stator resistance is given, rotor resistance is given, stator reactance is provided, rotor reactance is provided, and the magnetizing reactance is also given. Okay, the losses is given as 2450 watt. The mechanical load at a speed machine is synchronous motor is rotating at a speed of 1170 rpm. Okay, now we have to calculate these 8 parameters. Just write the numerical, just write the parameters, then I will explain the whole phenomena. Just wait. So the main the circuit diagram, or you can say the equivalent. So we have to first draw the equivalent circuit diagram of this machine. So the equivalent circuit diagram of the induction machine is this. That is prime supply voltage given this given, that is 480 volt. Then there is rotor stator resistance R1. R1 is given as 0.461 ohm. Then there is a rotor stator reactance or primary reactance, that is X1 is 0.507 ohm. Then there is a magnetizing reactance, or the core part of the machine, having the value Xm as 30.74 ohm. Okay. Then there is a current will flow. We don't have the value of I1 and we don't have the value of I1 and I2. Just we have the value of X2 as 0.309 ohm. Then there is a rotor resistance is also provided, that is 0.258. Here the slip is missing. Mainly the I1, I2 and S is missing. So first we have to find the value of the slip. So slip can be found only if we have the synchronous speed as well as the rotor speed. So that we have a speed, a mechanical load speed, or you can say motor is rotating with this speed. That means this is the rotor speed of the machine, or you can say Nm, and we have to find the synchronous speed. Okay, we have to find the value of the synchronous. We have to find the value of the synchronous speed as we have the value of frequency is given, the number of poles is given. So synchronous speed, just use the formula N is equal to 120 F upon P. 120 F. F is your 60 Hz and P is your 6 pole. Just use the concept of that formula. You will get the synchronous speed. So, just by putting the value, you will get 120 into F. F is 60 divided by 6. That means the RPM of this synchronous speed is 1200 RPM. This will become synchronous speed as 1200 RPM. Second is your sleep. Sleep you have the value of NS, you have the value of NR 1160. So you can find easily by using this concept or this formula, that is NS S equal to NS minus NM divided by NS. From there, just put the value of ns equal to 1200, nm equal to 1170 divided by 1200. That will give you 0.025. That means when you multiply this with the 100, you will get 2.5%. That is sleep is 2.5%. So this is the second part. Then there is a line current. Line for the line current, as we know, the phase current is given by V1 divided by ZIN. Z input, that means this is the Z input format. This is the Z input. We have to find the value of phase current for I1. So for that value, first we have to find the value of Z1, or you can say ZIN. You have the value of R1 and X1. From there, by using impedance triangle law, you can easily find the value of ZIN. So by using that concept, ZIN equal to R1 plus JX1. Okay. Now the total impedance of this machine, we have to find total impedance of the fine. We have to use this concept, this formula. Okay. So just use that formula. This is very basic thing that we have discussed in our second module. So from there you can easily grab this concept, that is how this is happening. Okay, here when you calculate this, these both are in parallel condition. So accordingly, we have to accumulate this concept. So by putting the value of R1, X1, R2, sleep, and X2 and XM, you have the value of ZIN or impedance at 9.57 plus J 3.84 ohm. That will give you the impedance of the value. You have the value of V1 as 480 volt, as you have the value 480 volt. Then we have calculated the ZIN as 9.57 plus J 3.84. So as the machine is also connected, as the machine is connected in delta connection, so the line voltage or the phase voltage is equal to 480 volt. So using that concept, you will get the phase current, that is I1 as this value 43.1 minus J 17.94. 17.4. As you can see, Z, this a real and imaginary term is in your denominator part. So just rationalize that format. When you rationalize, you will get this value I1. When you will get this value I1. And when you want to find the value of magnitude of this phase current, you will get this one under root 43.1 square whole square plus minus 17.4 ka whole square. Under that will give you the 46.6 ampere. Now, if you want to find the value of impedance angle, then you will get this minus 17.4 divided by 43.1. That will give you minus 21.9 degree. That will be tan inverse minus 17.4 divided by 43.1. That will give you the value of theta. So this is the basic thing that we have already calculated in our module 2. So we have the phase current, this value, that is 46.6 ampere. Now, if the question is asking for your line current, or you can say line current. So for the delta connection, as the question is in delta connection, the line current is equal to root 3 into phase current. We have calculated the phase current value as 46.6. Just multiply this 46.6 with the root 3 value, you will get the line current as 80.6 ampere. As 80.6 ampere. Okay, so 80.6 ampere is the line current of this machine. Okay, now the input, what is the value of the input power? You have the input power as this is your three-phase machine. This is your three-phase machine. So accordingly, if you apply that formula root 3 into V line IL cos theta, then you will get this formula. Either you can use this formula or you can use the phase value. As the line value is line current have the value root 3 into phase current. Just put the value of line current equal to root 3 into phase current, as this line voltage and phase voltage is equivalent. There is no relation between line voltage and phase voltage in three-phase delta connection. So there is only relation with stands with this line current, as line current equal to root 3 into phase current. So root 3 into root 3 will become 3. This VL become V phase, and this IL become I phase current. So accordingly, just put the value 3 into V1. V1 is your 480 volt. 480 volt is given. I1, you have the value of 46.6 ampere. I1 cos theta, just put the value of theta equal to minus 21.9 degree. Then accordingly, if you put the value, you will get the input power as 62.2 kilowatt. Input power as 62.2 kilowatt. This is the fourth condition. This is the fourth parameter. Now the air gap power. There is a formula for the air gap power. Air gap power we have discussed. Let me show you. This is the air gap power. In the previous classes, we have already seen that air gap power formula is the input power minus the your stator ohmic loss minus the stator ohmic loss, that will give you the air gap power. So you have the value P input power as 62.2 kilowatt minus 3. This 3 value exists for 3 phase. If you have the single phase machine, then it will be removed and it will remain for I1 square R1. I1 square R1, that will for single phase. But for 3 phase value, as there will be 3 RYB connection, so the ohmic loss in the stator part will be your 3 into I1 square R1. You have the value of phase current I1 equal to 46.6. The R1 have the value, as you can see, R1 have the value 0.461. So putting the value of the appropriate value of I1 R1, you will get the P gap or air gap power of the air gap as 59.2 kilowatt. Air gap power is 59.2 kilowatt, as this the input power is 62.2, but the air gap is 59.2. So there is a loss, and this loss you can calculate as because of this stator ohmic loss. Stator ohmic loss represent this value of the air gap formula. So this is the fifth point. Then there is another part, that is torque developed. The torque formula, that is power developed divided by the synchronous speed. So this is the torque developed can be found from this formula. The torque equal to air gap power divided by the synchronous speed, or you can see this synchronous speed, omega s, speed at which the machine is rotating, is given by this machine speed is given up 4 pi Fe upon P. I am not going to derive this formula. Just you have to remember this formula as 4 pi F upon P. So just put the value Fe as 6 years, P is number of poles is 6. So accordingly, if you put the value, there will be 40 pi. With involvement of 40 pi, just put the value P gap as 59.2 kilowatt. And using that formula and putting the proper value, you have the torque as 471 Newton meter. The torque have the unit Newton meter. Now the seventh one is a part of your output power in horsepower. This is the torque developed. This is the output power in horsepower you have to calculate. So the output power formula is the conventional power that is developed minus the rotational, that is the rotational power that is of your given formula. So this conventional power is given. This conventional power converted power is having the formula in relation with your air gap power, that is the 1 minus slip into air gap. You will get the converted power. So this converted power, just put the value, you will get, as you have the value slip 2.5%, or you can say 0.025, and the p gap have the value 59.2 kilowatt. Just putting the value, you will get as the converted power as converted power, and rotational power is already given in the question. Rotational loss is given as 2450 watt. So putting the value, you will get the appropriate output power as 55.3 kilowatt. As you can say, the air gap power is 59.2 kilowatt, but the output power is 55.3. So there is a total decrement of power from the input to the output power. As the input power is 62.2 kilowatt, then the air gap is reduced to 59.2 kilowatt, and the output power is becoming 55.3 kilowatt because of the losses that occurs in the induction machine. So the output power is this one, and the last part, the last is your efficiency. Efficiency is related with the output upon input. So output power is 55.3. Output power is 55.3, and the input power is 62.2 kilowatts. So just divide those term, 55.3 divided by 62.2, you will get the efficiency of the machine as 88.9%. So the efficiency is quite commendable for a proper induction machine. We can improve the efficiency of the induction machine by decrement the losses that occurs in the induction machine. So just using that concept, we have derived the various parameters that is involved in the induction machine. There is another examples that is related to the induction. There is another example related with the induction machine. So let us focus on those examples. So these are some simple examples that we have to use, because but just by using some formula we can find the different parameters. So here a question is given. There is another numerical. So this is very short type of numerical, so all of you must do the this type of numerical, because this can be uh, come in form of your MCQ questions also. Okay, so here the machine is given at 480 volt, 50 horsepower, three-phase induction motor is drawing 60 ampere. Induction motor is drawing means is taking this current from the source, as this is your motor. So it will not deliver the current, it will draw the current from the supply source. That way it will take the current from the supply source. The current that is taking the motor, that the motor that is taking the current from the supply is having the value 60 ampere, and it is doing that phenomena at 0.85 power factor at lagging condition. So this is the main rating of the machine is given in the upper first line, that is 480 volt is the supply voltage. Then the rating of the machine is 50 horsepower. Then three-phase induction motor is drawing at 60 ampere at 0.85 power factor lagging. The stator copper losses are 2 kilowatt. The stator copper loss, this is the copper loss, or you can say ohmic loss, is given as 2 kilowatt. The rotor copper loss, that is 700 watt. So you have to convert this 2 kilowatt into normal watt, or you can say this is 2000 watt. The rotor copper loss is 700 watt. Friction loss is 600 watt, and the core loss are 1800 watt. So these are some losses. When you accumulate this one, you will get 25, 31, 31, 50, 5100 watt is loss in the machine. So then we have to find the air gap power, converted power, output power, and efficiency of the motor. Okay, so we have the formula of different types of parameters. So just use that concept, use the formula, you will get your desired result. So the air gap is first we have to find the value of air gap power. So the air gap power in the previous condition, we have seen that air gap is related with input power minus the stator losses. Or you can say stator ohmic losses. So here also you have to for the air gap you have the value. This is the formula: air gap equal to input power minus your stator core loss, or you can stator core loss, or you can say stator copper loss. Stator copper loss. So just you have to find the value input power. Input power have the value this root 3 into VT IL cos theta. This is the supply voltage, and this is your this is the supply voltage at 480 volts. So just use the 480 volt. IL is your the current. Current is 60 ampere. Just use the value 60 ampere. Or theta have the cos theta is given as 0.85. This is the power factor. Put the value 0.85. You will get the input power. As this is no star connection or delta connection is given, whether it is connected in star connection or delta connection. So just put the value of voltage and current. You don't have to convert that line voltage to phase voltage or line current into phase current. So just put the value, you will get the input power as 42.4 kilowatt. So you have the value of input power as 42.4 kilowatt. Now you have the stator copper loss as 2 kilowatt. 2 kilo. This is the stator copper loss. The 2 kilowatt means this is 2000 watt. So the unit will be same as this is taken in kilowatt. So it must be in kilowatt. So 42.4 minus 2, that will give you 40.4 kilowatt. That is the air gap value of the induction machine. Then there is a converted power, as the value converted power is related with this formula, that is 1 minus slip into air gap power. We have to find the value of the slip in this question also. So we have to find the value of the slip. So there is another formula related with the converted power, that is air gap power minus your rotor copper loss. Air gap power minus rotor copper. We have the air gap power as 40.4 kilowatt. The rotor copper loss have the value, as you can say, rotor copper loss is 700 watt. Just if you want to convert this 700 watt into kilowatt, you will get 0.7 kilowatt. Or you can say, if you want to convert this AG air gap power as 40.4 kilowatt into watt, you will get 4400 watt. So just convert this 700 watt into kilowatt. It is done in this format. You will get the converted power output. Your converted power as 39.7 kilowatt. Now the next part is your output power. Output power have the value. The output power have the value converted power minus rotational power. converted power, or you can say this is the converted power. So this is the converted power. Rotational loss is given, friction loss and the core loss is given 1800. So by combination you will get 2.4, rotational loss is given as 2.4 kilowatt, and the converted power is 39.7. So just use that. So just use that concept. Just use that concept. You will get the output power as 37.3 kilowatt. The efficiency is output upon input. Output is 37.3 and the input is 42.4. You will get 88%. So these are the some basic numericals based on the induction machine. I am going to give you some. You should do this numerical by yourself. This is an example. This is an example of the machine. That is your 460 volt is given, 25 horsepower is provided. Then there is a 60 hertz value is given. Then four number of poles is 4 poles. Then star connection, induction motor has the following values. R1 is given, X1 is given, R2, X2, and XM. Mechanical loss is 100 watt. Core loss is 1 kilowatt. For a sleep, having the value 2.2%. 2.2% when you divide by 100, you will get 0.0022 value. That will be the value of the sleep. So just you have to find the first parameter, that is speed. Then there is a develop and output torque. Then there is a stator current. Then developed and output torque again. Here developed and output power. In the E portion, you have to find the value of developed and output torque. Developed and output torque. Then there is a power factor and efficiency is also you have to find. Developed and output torque and power factor efficiency you have to find. Okay. So these are the some basic, as we have already discussed two examples related with your induction machine. So I'm not going to very much in detail with this numerical. So how you can find, just I'm going to brief further how you can calculate. First, draw the equivalent circuit diagram of this machine. First, draw the equivalent circuit diagram of this machine, so that you can easily understand which part we have to find, and which part or which parameter is given in the question. So here you can say this is the R1 part is given. So this is the proper equivalent circuit diagram of the machine. V1, the supply voltage is given as 460 volt. This is the R1. R1 is the primary resistance is given. Then there is a X1. X1 is also given. Then there is a XM. XM is also given. Then there is a X2. X2 is also given. Then there is a R2. R2 is also given. R2 into 1 minus S. Sleep have the value. So all the components is already provided in the machine. Just I1 and IM is absent. You have to find the value of I1 and IM by using the Z impedance, Z input value. So R1 plus JX1, as we have discussed in the previous part, the value of Z input is this formula. Using the same concept, just you have to find the value of Z input here also. Z total, you will get the same function as this is your parallel function, R2 upon S plus JX2. This will come in parallel with JXM, and in the combination you will get that in series with R1 plus JX1. So accordingly, using the circuit theory concept, just you have to find the value of the Z total. Z total, you will get the value here also, that is input current as I1. So by using that same concept, you have to find the different parameters. So all of you must go through this numerical, so that you can easily understand the basic concept. So thank you for the today's class. Thank you very much.